Good morning. Talking about investing in infrastructure, this is a great example of what the United States did many years ago that has served us and the world actually in a great way. I first learned of the Panama Canal as a young student in college, but I didn't really gain an appreciation for how significant the project is and the significance to our profession. And I've learned that recently, and that's the message that I want to convey to you today. Few accomplishments of civil engineering have had as much economic, political, and social impact on the world as the Panama Canal. The canal changed the underpinnings of world commerce and transformed Panama economically and socially. Like the Suez Canal, it altered world trade routes and forever changed the economy of entire regions. By providing a cost-effective alternative to the railroads in the US, it fostered coast-to-coast commerce in the United States and gave both of our coasts efficient access to economic centers around the world. Prosperous ports of the southern shores of South America in the 19th century saw their trade activity curtailed while ports in Panama flourished. A true product of engineering prowess, the canal has been a source of pride for all of us for over a century. Often cited as an engineering wonder of the world, the project was made possible by engineers who applied their technical knowledge, their experience, and judgment to the daunting task of building the canal. Original construction entailed a multitude of challenges which compelled engineers to use the latest technology in civil, mechanical, and electrical engineering and in construction. The project included the biggest concrete structures, the deepest channel excavations, and the largest dam and reservoir made by man as of the turn of the 20th century. Theodore Roosevelt's Presidential Commission on the Panama Canal adopted the plan of an elevated waterway, a 50-mile-long, 90-foot-high bridge of water across Panama. As opposed to a sea-level canal, the idea reduced excavation volumes several-fold, provided flood control for the isthmus's rivers, and allowed the canal to operate entirely by gravity water flow. The original canal structures allowed simultaneous transit of ships in two directions. At the Atlantic entrance, the lock structures at Gatun are over 1 mile long and 400 feet wide. They include 3 chambers in each direction, each chamber being 1,000 feet long, 110 feet wide, and 80 feet deep. To accommodate challenging topographic and geologic conditions on the Pacific side, the designers laid out 2 lock structures at Pedro Miguel and Miraflores with equivalent combined dimensions and a small lake in between. The chamber sides are massive concrete gravity walls that contain large culverts. These pipes can fill or empty a chamber in less than 10 minutes, thus quickly raising or lowering the ships that transit the waterway. Anticipating all possible load combinations, engineers succeeded at building structures that have maintained tight tolerances and continue to function well for over 100 years. The designers used Rankine theory to calculate the earth pressures on the lock's walls and designed the lock's floor slabs for full hydrostatic uplift. Steel rods up to 30 feet long, spaced at 6 feet on centers, were used to anchor the slabs to the rock foundation. With periodic maintenance, they have resisted the uplift pressures since construction in 1910. In the absence of modern geotechnical engineering, the designers used experience, model tests, and early versions of the observational approach to design build the massive Gatun Dam. Dumping from rail cars and hydraulic filling, the most efficient technique for fill placement at the time, were used to place the 24 million cubic yards of material required to build the dam to a height of 110 feet. The success in Panama spurred the use of hydraulic filling for dam building until the failure of Fort Peck Dam in 1938 began to cast doubt on the technique as a safe construction method. Gatun Dam sits on a soft foundation of deep, geologically young, compressible, alluvial, and marine soils. Based on the strength of the soils observed in deep test pits and on large-scale model seepage tests, the designers anticipated that gentle fill slopes would be required to maintain stability and to prevent seepage from emerging on the downstream slope. During construction, the foundation and embankment yielded occasionally under the weight of the overlying materials, causing slides in the dam. Such slides drove the builders to buttress the structure as construction progressed and to spread the load by flattening the slopes to inclinations as gentle as 1 vertical to 14 horizontal. Over the years, the dam has performed very well, exhibiting modest settlements and minor seepage. Recently, it has been recognized that the methods of construction created inherent vulnerability in the dam to strong earthquake shaking. The owner now, the Panama Canal Authority, has thus undertaken a program to implement remedial measures to address this risk. But perhaps the most challenging aspect of the canal's original construction was the excavation of Gayler Cut, which allowed ships to cross the mountain ranges of Panama. As of 2005, construction and maintenance of the cut had required excavation of about 260 million cubic yards of rock to depths well in excess of 500 feet. About 35% of the excavated volume was from the many slides that plagued the excavation since its early stages and that made infamous the cut and the weak rocks that form its slopes. Intermittent slides in shales, siltstones, and other rocks of the Cucaracha and Culebra formations continue to this day and caused many closures of the canal. Those difficulties propelled research into the mechanics of sliding in the canal, which has led to a much improved understanding on the mechanisms of deformation and of the shear strength of fine-grained sedimentary rock. Today, extensive databases on the peak, fully softened, and residual shear strength of such rocks are widely available and used in design by all of us. Through application of the principles of modern soil mechanics and based on the advice of world-renowned consultants, the Canal Authority has instituted a landslide control program based on the observational method. This program has successfully allowed uninterrupted operation of the canal since 1986. In a nationwide referendum in 2006, Panamanians approved expansion of the canal, which had reached capacity and was unable to keep up with the increasing demands of maritime trade for larger, more efficient cargo ships. The expansion project included construction of 2 new sets of locks at the Atlantic and Pacific entrances, 4 dams, that's where I come in, to create a new access channel on the Pacific side, in widening and deepening of the Gayler Cut. Again, engineers applied the latest knowledge in science and engineering and overcame multiple design and construction challenges. Innovative designs were implemented to reduce in half the use of fresh water by the new locks, to prevent dam failure from unusual loads such as foundation fault rupture and ship grounding, and to excavate and dredge an additional 200 million cubic yards of soil and rock. To the credit of all of us, modern engineering and geology, no slides have occurred in the new excavations, and the canal expansion has been operating successfully since it was inaugurated in 2016. Cross your fingers. The Panama Canal is indeed essential to our global economy. Original construction and expansion of the canal posed great geotechnical challenges. Those challenges were met through careful planning, analysis, design, construction, but foremost, persistence by geotechnical engineers. Thus, the Panama Canal will remain as one of the major achievements of our profession and as a testimonial to the ingenuity and dedication of people like yourselves for years to come. Thank you.